This video is meant for Mrs. Rose's AB Calculus class on optimization. Optimize really just means that we want to either maximize or minimize something. It could be area of a shape, it could be volume of an object, it could be you want to minimize the cost in your manufacturing company. But ultimately you have an equation and you want to either have a maximum or a minimum. For example, we could be talking about a liquid form of penicillin manufactured by a pharmaceutical company, and it's sold in bulk at a price of $200 per unit. If the total production cost is C of x equals 500,000 plus 80x plus 0.003x squared, how many units of penicillin must be manufactured and sold to maximize the profit? So ultimately all we need to do is come up with an equation for profits. Well, profit, you are going to have the price that you're selling it per unit. So that's going to be 200 times each unit. But then you have to subtract the total amount of cost. So we're going to have to subtract all of this equation. So that we get revenue minus the cost. The point of this is we want to find a maximum profit. So we're going to do exactly the same thing that we've been doing recently with other functions. We are going to find critical value points and then do the first derivative test to see if it's a maximum or a minimum or neither. So we're going to take the derivative of p of x. What I'm going to do is I'm going to go ahead and distribute this negative sign and say 200 minus 80 is 120. So I'm going to get 120 minus 0 minus 2 times 0.03 is 0.006x. So we actually don't need that 0 part at all. And then, like we do for all critical values, we're going to set this equation equal to 0 and solve for x. So x is the quotient of 120 and 0.006, which is 20,000. So you have to make 20,000 units of penicillin in order to have a critical value. So then, to make sure that it is a profit, we need to do the first derivative test. And this interval is going to go from 0 to 20,000, because of course you're not going to make less than 0. And then from 20,000 to something more than 20,000, like infinity. So we can test something like 10, and we can test something like 50,000 units, and we're looking at p prime of x. If you plug in 10 into this, this is going to be a very small number, so we're going to get positive. And if you plug in 50,000, this is going to be a really big number, and it's going to be less than 0. So because the first derivative is changing from a positive to a negative, we know that we have a relative max. So the units that must be manufactured and sold to maximize profit is 20,000. And we write our conclusion sentence like this. P of x has a relative maximum at 20,000 units because p prime of x changes from positive to negative. So that was the answer for question A. And question B asks, what is the maximum profit? So we're going to just take our 20,000 and plug it in to our p equation. So we're going to have 120x minus 500,000 minus 0.003 20,000 squared. And when you calculate that, you should get $700,000 is the maximum profit. Alright, let's move on to the guidelines for doing optimization problems. These are on the notes handouts that you could print out from Edline, or you can write them down here. You need to make sure that all of your equations are in a single variable, so sometimes you have to write more than one equation, like area and perimeter, to try to get rid of one, and we'll do an example of that in a little bit. Determine an interval, so like we started our domain in the last problem at 0 and went to infinity, because you're not going to make less than 0 units, but you could make an infinite number, I guess. Take the derivative and then set it equal to 0 and find the relative maximum. You do have to find the absolute, but if you make 0 items, you're going to make 0 profit, and then you can't really test infinity. So I went ahead and just used the relative, but if you have a better defined domain, then you should do the absolute. For our second example, we're going to talk about a farmer, and he wants to enclose a rectangular area and divide it into 4 equal pins. So we're going to pretend like those are exactly equal pins. With fencing parallel to one side of the rectangle, which we have, and then what is the least amount of fencing he must use in order to enclose an area of 160 meters. So this is the one where we're going to have two kinds of equations. We have to have like an area, so x times y. Actually, let's not write that equation just yet. Let's make our diagram first. Okay, so if we have this pen set up, we need to be able to label our variables. So I'm going to label this side x, and then for the length, instead of just labeling it y, we have 4 equal units, or 4 equal parts. So I'm going to label each one of these y. And then in terms of perimeter, we have all of these are an equal x. So our area is not just x times y, it's x times 4y equals 160, and our perimeter, sorry about that announcement, guys. Our perimeter equation, we have to add up all of our x's and y's. So we have p equals 5x plus 8y. So once you have a diagram and your two equations, you need to determine the variable to be maximized, and optimize. We want to minimize p. So we need to change the perimeter equation to be with only one variable, like either x or y. The way you do that is you rewrite your area equation so that it's one of the variables equals the other. So I'm going to rewrite my area equation to be y equals 160 divided by 4x, and then I can rewrite my perimeter equation to be p equals 5x plus 8 times 160 divided by 4x, which does clean up a little bit. We've got 5x plus, let's see, 320 divided by x. Alright, now, and this is in terms of one variable, so we have p of x, and we want to find the relative extrema of this equation because we're trying to minimize it. So we should take the derivative, set it equal to 0, and solve for x. Now technically x equals plus or minus 8, but length is always positive. So we're really only talking about positive 8. So when we go do our intervals, we can't have less than 0 as our shortest side, and you really can't have more than 40, so we're going to break up our intervals at 0, 8, and 40, and then we can do our test values, and we're trying to figure out what's the derivative of our perimeter equation. When you plug in 1, you're going to get a negative, and when you plug in 10, you're going to get a positive, so that we do get a relative minimum at x equals 8. So the question asked us what's the least amount of fencing he can use. So if x is 8 and y is 160 divided by 4 times x, then y is going to equal 5, and then our perimeter is going to be 5 times 8 plus 320, oh, I guess divided by 8, okay. And then we're going to get 40 plus 49, which is 89, and the units is meters. Be sure to check out the other 2 videos on optimization, and I'll see you in class.